Computers and hardware. Computers and hardware form the backbone of modern technology, evolving through decades of relentless innovation to become the sophisticated systems that power every aspect of our digital lives. The journey of these devices is one of transformation from bulky, room-sized machines performing simple arithmetic to elegant, compact systems capable of executing billions of operations every second. Over time, hardware design, architecture, and manufacturing techniques have advanced in tandem with our growing demands for speed, efficiency, and reliability, resulting in components that are not only smaller and faster but also more energy efficient and powerful. From the beginning, the development of computers has been driven by the need to solve complex problems and make sense of vast amounts of data. Early computing machines, which used vacuum tubes, faced significant limitations in terms of speed and reliability. These early devices were prone to overheating and required vast amounts of power, while occupying entire rooms. The subsequent invention of the transistor in the mid-20th century marked a turning point, as these semiconductor devices offered a pathway to miniaturization and lower power consumption. Transistors quickly replaced vacuum tubes, allowing computers to become smaller, more reliable, and far more efficient. This shift to semiconductor-based technology paved the way for the integrated circuits that now serve as the foundation for virtually every modern electronic device, underscoring a remarkable leap in both performance and manufacturing capability. Central processing units, CPUs, have evolved dramatically in design and functionality over the years. Early CPUs were limited in terms of instruction sets and clock speeds, but with the continuous development of microarchitecture and fabrication processes, modern microprocessors incorporate billions of tiny transistors on a single chip. The evolution from simple, single-core processors to advanced multi-core systems has enabled computers to handle parallel tasks and process complex workloads in real time. Techniques such as pipelining, speculative execution, and caching have further enhanced performance, ensuring that the CPU remains the most critical element in determining the overall speed and responsiveness of a computer system. This continuous refinement in CPU architecture not only supports daily tasks like web browsing and document editing, but also empowers high-performance computing applications, such as simulations, data analysis, and artificial intelligence. Alongside CPU advancements, graphics processing units, GPUs, have emerged as specialists in handling parallel computations, substantially impacting industries that require the rendering of complex images and data visualization. Originally developed to accelerate 3D graphics in gaming, GPUs now perform general-purpose computing tasks that leverage their massive parallelism. In applications ranging from scientific research to cryptocurrency mining, GPUs excel at processing many parallel tasks simultaneously. Their integration within modern computer systems illustrates how specialized hardware can coexist with general-purpose CPUs, working together to meet the demands of diverse applications. The evolution of GPUs has also fueled the growth of machine learning, providing the necessary performance to train and run deep neural networks that have transformed fields such as natural language processing, computer vision, and autonomous systems. Memory and storage technologies have experienced similar leaps forward, offering increasingly larger capacities and higher data transfer speeds while consuming less power. Random access memory, RAM, crucial for storing data that the CPU accesses in real time, has transitioned from early forms like magnetic core memory to modern dynamic and static RAM, which offer unprecedented levels of speed and density. Meanwhile, storage has shifted from mechanical hard disk drives, HDDs, to solid-state drives, SSDs, that use flash memory. SSDs provide faster read and write speeds, lower latency, and enhanced durability since they lack moving parts. The combination of faster memory and storage solutions underpins the rapid execution of applications, enables real-time data processing, and supports the high bandwidth required for multimedia streaming and cloud computing. As developers continue to push the limits of storage density and speed, emerging technologies such as non-volatile memory express, NVMe, and persistent memory offer exciting possibilities for further reducing bottlenecks in data-intensive environments. Motherboards serve as the central nervous system of computer hardware, facilitating communication between the CPU, memory, storage, and peripheral devices. Over the years, motherboard designs have become more integrated and efficient, featuring multiple high-speed connectors and interfaces that allow for rapid data exchange across various components. Modern motherboards support a broad range of connectivity options, from high-speed USB and Thunderbolt ports to PCI Express slots that accommodate the latest GPUs and expansion cards. These interconnected platforms enable a harmonious orchestration of a system's operations, ensuring that each hardware component can work in concert with the others to deliver reliable performance. Innovations in motherboard design also focus on power management and cooling, critical aspects for maintaining system stability as components continue to shrink and operate at higher speeds. Cooling solutions have become an essential consideration in modern computer hardware design. As processing speeds increase and components become denser, the heat generated by CPUs, GPUs, and other components can become a limiting factor in overall performance. Advanced cooling techniques, such as liquid cooling and heat pipes, have been developed to dissipate this heat efficiently. These methods not only maintain optimal operating temperatures but also prolong the lifespan of components by preventing thermal degradation. Effective cooling solutions are critical for sustaining high performance in gaming rigs, workstations, and data centers alike, ensuring that systems remain stable under demanding computational loads. The evolution of cooling technology underscores the interconnected nature of hardware design, where improvements in one area can necessitate enhancements in another to support the overall functionality of the computer. Modern computer hardware continues to be shaped by the ever-growing demands of emerging technologies such as artificial intelligence, machine learning, and virtual reality. These fields require not only increased processing power but also highly specialized hardware capable of handling complex, data-intensive tasks. The integration of specialized processing units, such as tensor processing units, TPUs, and field programmable gate arrays, FPGAs, into mainstream systems is enabling a new era of computing where tasks such as image recognition, natural language processing, and predictive analytics can be executed faster and more accurately than ever before. As these technologies mature, they are likely to drive further innovations in general-purpose hardware, creating a feedback loop of progress that accelerates the development of even more powerful systems. Connectivity has also been revolutionized by the advent of high-speed networking hardware. Advances in Ethernet and wireless communication standards have dramatically increased the rate at which data can be transferred between devices, forming the backbone of modern data centers and cloud computing architectures. High-speed interconnects and distributed storage solutions allow computers to work together in complex networks, facilitating tasks such as large-scale simulations, content delivery, and the deployment of global applications. The networking hardware that interconnects these systems has evolved to support higher bandwidth and lower latency demands, enabling seamless communication across vast distances and powering the modern digital economy. The relentless drive for performance and efficiency in computer hardware is fueled by ongoing research in materials science and quantum mechanics. As silicon-based technologies approach their physical limits, researchers are exploring novel materials like graphene and transitioning to alternative paradigms such as quantum computing. Quantum computers, leveraging the principles of quantum mechanics, promise to solve problems that are currently intractable for classical machines, including complex simulations and cryptographic challenges. While quantum hardware is still largely experimental, its potential to radically transform computation is sparking significant investment and research efforts, hinting at a future where entirely new hardware paradigms coexist with traditional computing technologies. In addition to raw performance enhancements, advances in computer hardware are also making systems more energy efficient and environmentally sustainable. As the global demand for computing power grows rapidly, energy consumption has become a major concern for industries and data centers. Innovations in low-power processors, efficient cooling methods, and power management systems are critical for reducing the environmental footprint of modern computing infrastructures. Achieving a balance between high performance and low energy consumption is not only beneficial for lowering operational costs but also essential for meeting global sustainability targets. These energy-saving advancements demonstrate a convergence between technological progress and environmental stewardship, highlighting the broader societal impact of innovations in computer hardware. Security in computer hardware remains a critical area of focus as well, with emerging threats requiring ever more sophisticated defenses. Hardware-level security features, such as trusted platform modules, TPMs, and secure boot processes, help ensure that systems are protected from low-level attacks and unauthorized access. These features are increasingly integrated into consumer devices as well as enterprise systems, providing a foundational layer of security that undergirds modern operating systems and software applications. As cyber threats continue to evolve in complexity, the integration of hardware-based security measures is essential for safeguarding sensitive data and maintaining the integrity of computing systems. This commitment to hardware security coexists with the broader imperative of designing systems that are both powerful and resilient to digital threats. The remarkable evolution of computers and hardware reflects an ongoing dance between innovation, performance demands, and physical constraints. What began as room-sized machines built for simple calculations has transformed into a landscape of diverse technologies that power everything from smartphones and personal computers to vast data centers and emerging quantum systems. The interplay between microprocessor design, memory technology, connectivity, cooling solutions, and security measures continues to drive the field forward, ensuring that our digital infrastructure remains robust, efficient, and ready to tackle the challenges of tomorrow. Every leap forward in computer hardware design not only redefines what is possible but also opens up new horizons for research, industry, and everyday life. As computing systems become more capable and energy efficient, they empower innovations across numerous disciplines, from medical research and environmental monitoring to virtual reality and autonomous vehicles. Ultimately, the evolution of computers and hardware represents a testament to human ingenuity and the endless pursuit of knowledge. Each improvement builds upon the achievements of previous generations, forming a cumulative legacy that continues to enable new forms of human expression, discovery, and connectivity. This never-ending journey of innovation, driven by relentless research and practical application, ensures that the future of computing will continue to surprise and inspire, profoundly shaping the world in ways that are only beginning to be imagined.